The Australian curriculum, Earth Science in Year 9, Plate Tectonics. Pretty good topic, one of my favourites. So here we have a lava fountain. I'm pretty sure it's in Hawaii. That's pretty cool. And so we've got probably some obsidian here. Some of it would be basalt, but that's looking like it's going to cool very, very quickly. So most likely obsidian. Might not be as beautiful and glassy as most things. There's going to be a lot of air trapped in that, I reckon. If you got an idea about where this is, you're pretty clever. It's the East African Rift Valley. So that's a bit where it's a line where lakes are filling up cracks that are formed when we've got some rifting going on there. You'll learn more about that soon. So the Australian curriculum outcomes are here. Be my guest if you want to read them closely. The only thing I probably want to talk about here is the fact that convection currents, I've crossed it out because it's really outdated theory. It goes back to the 90s to do with how long it's been outdated. Its origins are well before that. We know now that certainly there aren't big convection currents in the mantle. There's mixing, but heat loss is not the driver of plate tectonics. It's actually gravity. We'll look at that at some stage later on. So the basic outline of this unit, probably the most interesting thing about this is we're going to look at these case studies. They're pretty cool. One that I've added recently is Australian Alps. That story's pretty fun. Maybe even some stuff about Albany and Western Australia, I'm not sure. That's a video that you won't have access to. Anyway, so structure of the Earth. At Year 9, we're going pretty basic. Even Year 11, Earth and Environmental Science isn't much bigger than this. So inner core, outer core, 3 and 4 are the mantle. So the lower and the upper mantle, and then 5 is the crust or lithosphere. The asthenosphere is the upper mantle as well. Technically, lithosphere and crust aren't exactly the same thing, but let's not worry about that. Oceanic crust, we're looking at about 8 kilometers thick. There are spots where it is 0, where there is mantle exposed. And again, continental crust is usually about 40 kilometers, but anywhere between 0 and 75 kilometers thick. We can see that this is not to scale. That's 75 and this is like 6,000. That's not quite right. Interesting to note that everything is solid except for the outer core, which is liquid. I'll put this link in the description. I'll put the links in order too. So this is more to scale. So you've got a really, really thin crust. It might not look like from looking at this, but the lower mantle makes up the vast majority of the Earth. Sorry, the mantle, not the lower mantle. Makes up the vast majority of the Earth's volume. Even though it looks pretty even here, when we do a big circle around this, we can see that the circle where the mantle is much bigger than anything else. So our thicknesses are here. So 0 to 80, 0 to 35. So the lithosphere is the crust plus the upper mantle. And that's just to do with how that layer of the Earth functions. Then we have the mantle between 35 and close to 3,000. The mantle's made up of the asthenosphere, upper mantle, lower mantle, and just the top of the mantle is part of the lithosphere. And we have the outer core and the inner core. So evidence related to the structure and composition of Earth comes from a number of sources, so we're not just making it up. So earthquakes tell us a fair bit. We've actually got rock and mineral samples from the inner Earth. They've come up with melted mantle, so they kind of get chipped off and picked up and come for the ride. They're really high temperature minerals. They form at quite high temperatures, so the temperature of a magma moving through the Earth is not enough to melt them, so they stay there. We've also got zircons, which is the type of mineral, and they're incredibly tough. They're like little bits of sand, but we can actually date them to see how old they are and what their composition is. Asteroids and meteorites that have come from our solar system essentially have the same overall composition as our planet. Our solar system, and even our solar system, that's probably a better way of putting it. The planets are quite homogeneous, particularly the rocky planets, to do with what they're made of. Composition of the moon is another one. when they got to the moon and got rock samples. In fact, one of the people who worked, the old professors in the A&E geology department, he was one of the guys waiting. I think his name was Ross Taylor. He was waiting for the moon rocks when they got back from the 1969 Apollo 11 landing, because they brought rocks back, and they were all excited. And they said, "Look, you got to tell us what these rocks are made of, really, really fast." And they were just basalt. So they weren't very exciting. Pretty much exact same composition of the Earth. And we have a magnetic field, and that's really big evidence. So the magnetic field will only form if there's a dynamo. So that means outer core, a dynamo is moving, so moving iron, creating an electric field. And with an electric field, you're going to get a magnetic field. Yep, that one's interesting. That's on YouTube as well. I'll put that in the link. So the chemical composition of Earth is 32% iron. So overall, mostly iron and oxygen and silicon, magnesium. So apart from that, there's, other elements in there. Like 8% or 7.6% of those elements is still a significant amount of those elements, given the sheer size of Earth. But we can see that the Earth's crust is very, very different in composition to the average composition of the Earth. We can see that the crust is 46% oxygen. And we can see that is 28% silicon. So these two are definitely there. But we can see that's only 6% iron. That's unusual. Our whole planet is 32% iron, but the crust is only 6% iron. So it's very different chemical composition going on. So we're looking at 74% of the crust is oxygen and silicon, but they only make up 45% of the Earth. So there's a bit of a disparity there. Here's just some data on those numbers. Probably a thing that... So we can see that the mantle has a big jump in magnesium compared to the crust, and big drop in aluminium. Pretty similar oxygen and silicon. Pretty similar iron. The core is 80% iron and nickel. There's also obviously other atoms or other elements in the core. They just happen to be in there. Like, it's not pure iron and nickel. Geology doesn't quite work that way. Okay, which elements differ significantly? Yep, why is so much of the iron in the core? If you said density, you are correct. The Earth used to be a little bit molten, and when it was molten, had the opportunity for elements to move. So the denser elements, and given that a lot of the Earth, 32% is iron, a lot of iron ended up in the core. So it's kind of essentially sunk from all directions towards the middle. So continental crust, mostly igneous rocks, basalt and granite. It's relatively buoyant. Now you might think it's strange calling rocks buoyant, but relatively buoyant, so less dense. So oceanic crust is mostly made of basalt, and that's formed at mid-ocean ridges. Also underwater volcanoes, but not granite, and it's because the crust that's forming at the bottom of the ocean doesn't have time to cool slowly necessarily, and it's not as thick as the continental crust. Okay, can't put that one there. It's not on YouTube either. So volcanic activity results in your crust. So what do you think is younger, oceanic or continental crust? Good question. It's oceanic crust. What does it mean to be geologically active? Well, that means there's volcanism going on. Or also plate movement, but if there's plate movement, there's going to be a volcanism. So, hypothesis about the change... That's my dog. Hypothesis about the change in temperature as you go towards the centre of the Earth. If you said it gets hotter as you go towards the centre of the Earth, you'd be correct. What about the change in pressure as you go towards the centre of the Earth? Again, if you said pressure increased as you go towards the centre of the Earth, you'd be correct as well. A lot of rock sitting on top of you At the surface, we have 1 atmosphere of pressure. For example, if we go 10 meters under the water, we have an extra atmosphere of pressure. How do temperature and pressure affect the density of something? Now, this is interesting. So pressure makes something more dense, increasing temperature makes something less dense. So as we go towards the center of the Earth, the pressure is trying to make things denser, yet the temperature is trying to make things less dense. So we've kind of got two opposing forces there. I'll give you a hint, pressure's winning. So we can see rapid increase in temperature through the asthenosphere, steady increase until we get to near the outer core. Now the outer core is liquid, so it's far better at transferring heat. So we can see that's why that increase in temperature kicks on again. The outer core is fairly constant, and the inner core is just completely solid and almost isothermic, so the same temperature through the whole thing. Pretty hot down there. So density, this is interesting. So we can see that this is not a continuous or consistent line at all. So this is more dense up the top, this is less dense down the bottom. And this is just the radius of the Earth. So as we get out to that 6,000 kilometers. And the core's obviously that's at 0. So we can see that the density of the core is fairly consistent. But then we can see there's a definite change going to the outer core. For this reason, it means that the inner core will always stay underneath the outer core. Then we can see the outer core, it's liquid. We can see there's a gradual density change until we get to the core mantle boundary, and have a look at that. Massive change in density, almost half. The lower mantle is almost half as dense as the outer core. For that reason, the mantle will always float on the outer core. It cannot sink into it. And then we have the mantle, pretty consistent change in density. And then we have some distinct points, particularly here. So the MOHO discontinuity, that's pretty significant. Looking at the density of Earth's layers, we can see, so grams per cubic centimeters. You can compare that to water, and water is 1 gram per cubic centimeter. So we can see that the continental crust is 2.7 to 3 times as dense as water. We can see that oceanic crust is 3 to 3.3 grams per cubic centimeters. So oceanic crust is denser than continental crust, and that's important. We can see that the mantle starts off at the same density as the oceanic crust, however, is denser than the continental crust. And we can see that here's this massive change between the mantle and the outer core, and then a slight change between the mantle, the outer core and the inner core. We can see that there is almost an overlap between oceanic crust and the mantle.